A window through time, charting the faceless names who built the Old South. The flow of fire, revealing the boundaries of turbulent combustion. A quantum view, probing ups and downs in atomic detail. Orbital insights, firing up students about molecules in the making.
It's a job of the historian to bring order out of the chaos that's the past. I felt like a detective. I think that's exactly what a historian is. He's on the trail of trying to find the truth.
First settled in the mid-1700s, Edgefield County, South Carolina represents a microcosm of the American South. Edgefield's long history is still evident in the churches and graveyards, slave quarters, and antebellum mansions that dot the countryside. But to find out what really happened in the community of Edgefield before and after the Civil War, historian Orville Vernon Burton turned to an unusual resource, the historical data records of the United States Census Bureau.
They're all there, the stories are hidden, in particular when you put them together with the census records where you have some sense of where these people fit into the social structure, where they lived, who their relatives were, what resources they had in terms of wealth, in terms of schooling, that you begin to put together a much more complete and holistic picture of the society.
Combining data from the census returns of 1850 to 1880 with more traditional archival materials, Burton was able to analyze the social history of 19th century Edgefield County.
Well, I'm reading these letters to try to find out what's going on and put the story together. When I saw General Hampton the other day, he was serious. Need a magnifying glass to figure it out.
In 1985, Burton published his sometimes controversial findings in the book, In My Father's House Are Many Mansions.
By looking at the demography and the distribution of where people lived and whether it was a male or female who was head in the household, I was able to show that there was a spatial pattern to where women headed households. Both white and black women had more households in towns. After Reconstruction, after that, black men are excluded from the town economies, and particularly any of the jobs, and the only thing they can do is, in fact, farm.
Employing a mainframe computer to analyze the census data enabled Burton to establish demographic movement in the community. However, creating his own program to link the separate census returns proved both difficult and time-consuming.
The census returns are not just the population returns we've been talking about, but you have agricultural returns. So you can take, and they're separate. You also had slave returns listing slaves. You had mortality returns. You had social science, social statistics returns, which talk about the number of people in jail. You had manufacturing returns that talk about people who are doing pottery.
Recognizing the need for more powerful computers and customized software tools to speed up his studies, Burton is now collaborating with a team of researchers at NCSA. They are prototyping a database management system, a window into the history of the United States.
Many scholars in the social sciences and the humanities in particular are somewhat wary of using computers because they just aren't exposed to them in the same way that people in the biological or physical sciences would be. So what we're trying to do is make this as accessible as possible so that it would have as wide an audience as possible and be as used as much as it could be.
The project that we're starting with is data from 1850 to 1880. We are taking then all of these census databases and putting them into a real relational, extended relational database system running on a Sun Spark station, and taking also the output from that program, and then working with that database to set up a system that will have a great deal more power and flexibility.
Barbara Mihalis develops database management systems for a variety of scientific disciplines. Even so, creating a so-called expert system to investigate the handwritten census returns quickly and easily presents a formidable challenge.
On the census schedules, people apparently do not change their genders, but they do change their names. And I think a lot of the slaves, when they were released, changed their names. Women changed their names routinely. We have an initial program that we're starting with that's based mainly on name matching. And then one of the big efforts that we will be doing over the next few months is incorporating some of Vernon's knowledge about, it's kind of detective knowledge about if you have matching up information of certain sorts, it means that this is the same person in two different schedules. And so it's almost like developing an expert system.
For Vernon Burton, the ultimate goal of the project is to have the census data from 1790 to 1920 online and available to a nationwide network of users.
Does it make a lot of difference in how people approach history? They will then use the resource, they'll be able to get to it and ask simple questions like, you know, what was the average wealth in a community? How many people were poor in a community? How many people owned slaves? They want to know programming or statistical language or statistical packages even. And this is one of the hopes that we're trying to bring out of this project, one of our dreams.
Igniting a swirling vortex of fuel and oxygen releases enough energy to propel rockets into space, airplanes through the sky, or cars along the highway. But the efficiency and power of the engines are critically dependent on the rapid and turbulent mixing of oxidizers and fuel. Professor Ahmed Ghonim, a mechanical engineer at the Massachusetts Institute of Technology, is employing computational fluid dynamics, or CFD, to construct software that simulates turbulent flow and combustion. By analyzing scientific visualizations depicting the turbulent vortex structures, Ghonim hopes to understand the fundamental principles underlying turbulent combustion.
Combustion systems produce pollutants because they cannot burn all the fuel we put in them within a short period of time that we have within that system. And by learning more about the fundamental mechanisms that govern turbulent combustion, we hope to be able to achieve complete burning within a short period of time so that we gain higher efficiency and reduce the toxic pollutants put out by the system.
Ghonim is collaborating long distance with Chris Kent, engineer at Ford Motor Company's research laboratory in Dearborn, Michigan. In the laboratory, Kent studies turbulent fluid dynamics in car cylinders, while Ghonim develops computer codes that simulate the same dynamics. The goal is to develop software tools for predicting and optimizing the performance of new engine designs at Ford.
We're interested in how the geometry of the intake port, for example here, affects the flow as it goes into the combustion chamber, into the cylinder during the intake stroke. We found that the nature of the flow in the cylinder has a profound influence on the combustion itself, primarily the speed of the combustion.
Employing the water analog flow visualization device developed at the Dearborn laboratory, Kent observes, measures, and videotapes the turbulent eddies produced by different intake port designs. Water simulates the fuel-air mixture, and polystyrene particles suspended in the water make the fluid motion visible.
This is, in a sense, an analog computer in that it gives us the correct solution to the problem without any assumptions about the equations of motion or any simplifying assumptions. The idea of an optimum design would be to have lots of very small eddies at the time the spark occurs. The challenge is in producing the turbulence at that time.
The geometric parameters of Kent's water analog experiments are provided to Ghonim at MIT. Ghonim and graduate researchers then numerically model the flow processes. To realistically simulate all the interactions requires the speed and memory of a supercomputer.
If you look typically into the airflow inside the car engine, You find things changing very rapidly as you move from one point to another point 1 millimeter away, or even less than 1 millimeter away. As the turbulence becomes more intense to achieve mixing, these variations become even more rapid and more strong. So we need to resolve the flow field that we're studying at many points in space.
A high-speed network link to Urbana, Illinois enables GONIM to carry out the computations on NCSA's Cray YMP. By creating graphic representations of the flow patterns from the computer simulations, GONIM and Kent can compare the accuracy of the computational results with the experimental data.
It's very much an evolutionary process, and it does require working both on the numerical methodology as well as the experiment simultaneously and in a very interactive way. We do a set of calculations, we get results from the experiment, from the laboratory, and we compare them. And from that, we learn a little bit more about the problem we're studying. We also learn whether the level of complexity and detail of our computation is sufficient or not.
But once we are able to get a good comparison between our experiment and the computational work, we'll proceed to more complex and more realistic cases. The use of computational fluid dynamics as a design aid is the long-term goal of this work. The advances in computers and speeds and memory is progressing at such a rapid rate that I think within a matter of 5 to 10 years we can expect to use this sort of technique in a very significant way in our engine design and development process. And this will allow us to shorten the design and development cycle, will allow us to reduce the number of times that we build an experimental prototype engine and test it along the way towards optimizing its performance.
For GONIM, the collaboration with Kent and Ford represents just one of many possible applications of computational fluid dynamics in the design of more powerful, fuel-efficient combustion devices.
To understand how electrons behave within the crystalline structure of a semiconductor, theoretical physicists created this scientific visualization. But to actually see a semiconductor's surface with atomic resolution or build circuitry on the atomic scale has been their dream for years. And now, at the Beckman Institute for Advanced Science and Technology, an instrument called a Scanning Tunneling Microscope, or STM, is enabling researchers to realize their goals at last.
Scanning tunneling microscope is a tool that allows you to observe the surface of a conducting material with atomic resolution. And the way that works is you take a very sharp metal probe and you bring it to within a few atomic diameters of the surface, and then you apply a voltage between the two, and that potential difference causes electrons to tunnel through the barrier that's there.
By monitoring the so-called quantum tunneling current of electrons between the tip of the probe and the sample surface, data describing the three-dimensional placement of atoms on the surface can be obtained.
When you're over an atom, the distance between the probe and the surface is smaller, so the current is higher. And when you're between atoms, the current is lower. So as you scan, the current is modulated in a very strong manner that can be recorded, and then a computer can take that modulation current and construct an image on the video screen. And that's a real-time picture of what the surface looks like in 3 dimensions.
Here, lighting readies a sample of gallium arsenide inside an ultra-high vacuum chamber designed to purify the sample surface and keep it free of atmospheric contamination. Once the sample is within tunneling range, scanning begins. During the experiment, a small amount of oxygen will be introduced into the chamber. The scanned data from the slowly oxidizing gallium arsenide is sent through a high-speed network to NCSA's convex C240 for rapid image reconstruction. This allows observation of the oxidation process as it happens.
A personal computer forwards it over to the convex across the network. The convex will do the image processing and all the computing that needs to be done on the image, and then the cleaned up image or the processed image then gets sent back over the network to the scientist's workstation.
Lighting employs NCSA's ViewIt software, a multidimensional image analysis package customized to manipulate the STM data with the push of a button. He's collaborating with NCSA's Meta computer design team to couple the convex more tightly with the STM's computer, ultimately allowing remote control of the STM through the convex.
So you can have the scientist anywhere in the country controlling the microscope instead of having to sit in Joe Lighting's lab in order to do it. So it allows remote control of the microscope, which is really what our group is trying to do. We're trying to set up, you know, distributed control of these instruments. And so all of a sudden a networked supercomputer with a personal computer has changed from two boxes with a link between them into one functionality, one logical computer. And that's the idea behind the metacomputer concept.
Not only can the STM image real-time atomic surface interactions, but the tip of the STM probe can be used to move atoms around, etching the surface in a process known as nanolithography. Professor Carl Hess, director of the National Center for Computational Electronics, is collaborating with Lighting's group to build a nanoelectronic switching circuit called the T-structure quantum modulated transistor. The device exploits the wave-like nature of the electron at the atomic scale.
All you need is a T-shaped structure, which of course can let electrons propagate, and you need to be able to change the effective electrical lengths of the sidearm. The electron has a wave-like nature if the structure is small enough. So the wave comes in from the left, propagates in the sidearm and is reflected, and then interferes with the incoming wave. This interference is such that a peak of the wave meets a value of the wave, it destructs. And so the electron, what that means is the electron does not propagate. There's no current conducting. And then if you change the effective lengths of the sidearm, the wave can construct, and then the current can propagate in the main arm. So you switch on a current. We have mechanisms, we have ways of making it, so we are progressed from a physicist dream to an engineering dream. It's still a dream, but we're one step further.
Utilizing the STM to both build and observe the viability of the T-shaped transistor and other devices opens one more door to the new frontier of nanotechnology.
By the end of this decade, devices are going to start approaching the size at which new lithographic tools are going to be necessary to actually make them. Now, we don't envision scanning tunneling microscope as being a commercial production instrument for making huge numbers of small devices, but what we do envision is that we should be able to make small numbers of devices, see how they work, optimize their design, and provide a basis for other techniques that would be useful for mass producing them when these techniques come into existence.
I think teenagers are visually and audially oriented, very much. Like looking at cool pictures and listening to music and things like that. So I think that the visualization is very important.
At Centennial High School in Champaign, Illinois, these chemistry students are interacting with computer animations that they generated at NCSA. The teenagers are not only intuitively learning chemistry, they're also helping to bring high-performance computing into the secondary school, a technology that can make learning science both interesting and fun.
Visualization, the visual mode of exploring new information, can be very, very useful for students to start on a new field. So the thought of extending to education, particularly pre-college education, the same methods that high-performance computing allowed researchers to use is a natural role for NCSA.
In the spring of 1991, research chemist and educator Nora Sibeli and Centennial High School teacher Barry Rao carried out an experiment. They introduced high school chemistry students to the tools and techniques of computational science at NCSA. Logging onto an NCSA supercomputer, the students spent the day learning how to model, visualize, and animate the electron orbitals of simple molecules.
But if you do it within the context of the classroom with lots of discussions before, if you do this as science is done, then the learning of the mathematics, the learning of the theory is anchored in something that the student can visualize, can feel. It changes the way the students deal with the questions, and it's very hard to learn mathematics or to learn abstract concepts if you don't know what they are for.
And all of chemistry revolves around the shape and the size and the location and the orientation of particles that we'll never see. So we really need to be able to simulate that. And you can do that with visualization. There's not much electron density here. But now you've gotten within a distance at which the nuclei are beginning to attract the other electrons.
The students' response was so enthusiastic that Sabelli and Rao initiated Visualization in High School Chemistry, a new project that already reaches several other schools in Champaign County. The goals are twofold: prototype classroom activities and materials that tap the power of computers and visualization to bring chemistry to life, and incorporate these new resources not only into chemistry, but into the high school science curriculum as a whole.
I would say the characteristics of the project are that the teachers are setting the pace. We provide the hardware, the software, some of the programming, the expertise, this is my field, but the teachers put the educational content, how they would use it, what the students would do.
We saw that there was a real problem with students understanding why molecules and atoms have the shapes they have. We decided as a group that that would be the first project we would explore, and we are close to finished with that.
Rao's current chemistry students attend another day-long workshop at NCSA. Again, the students employ an NCSA supercomputer, but this time the software interface to the machine, modified by project coordinator Igor Lifshitz, enables the students to easily generate electron density maps of small molecules and atoms.
We just loaded up the two different atoms and set them into motion together. It was really neat, except it turned out they have two different orbitals. They're both p orbitals, and they came together like this instead of how you'd think they'd come together end to end or side to side. So it was kind of interesting, the bonds they formed.
We're still not where we want to be. There's still more than 40 steps in the little recipe, the little procedure that the students follow. And eventually, we want to make it fewer than 5 steps, so that what they'll be doing is collecting data and analyzing data, and so to speak, doing science.
So, wait.
Not only are the students learning how computational science is done, as end users, they're doing a lot more. They are helping to fine-tune the tools that animate the molecules, including the software interface to the supercomputer.
I think it's important that the high school students have other high school students writing it, because they're in the same mindset, and they know when the program is written by another high school student that he has their interests in mind as well.
Another important aspect of the project is the creation of an educational mentoring network that reaches from NCSA research scientists to the high school teachers, and from NCSA's undergraduate support staff to the high school students. And for the high school teachers, observing the students' responses to computational science spurs the development of new teaching methods. After the software interface design is complete, the project will expand to include a nationwide pool of high school teachers. From start to finish, the involvement of high school teachers will remain vital for the success of the project.
Every time I get up in front of a classroom, or even every time I talk to a student about chemistry, it goes through my mind, what would it look like if we could model this? And what kind of bonding is there going to be here? And then I talk to the student about that. So see, that's the key, I think, to teaching teachers how to use this procedure, how to use our project, is that it stimulates them to do something else.
Ultimately, the hope is that introducing scientific visualization into the high school classroom will spark teenagers to pursue not only chemistry, but other sciences in their college careers and beyond.
We are visual learners as human beings, and if you can start exploring a field visually and get some intuition about what goes on, then you can formalize it afterwards. And that is something that can help us attract and make science education better.
If you would like to know more about the activities featured in this program, please contact NCSA at the following address.